Welcome everyone. So this is our 40th live stream geometry, and we already have 4 other people in addition to me on the session. So I've been doing a few mock contests lately. So today I wanted to do one called the GOWACA. So that's GOWACA. It stands for Geometry Olympiad without a cool acronym. So it was created by a user on AoPS. MP8148. So I'm not sure too much about him or her, although actually I know it's a boy because I read his blog. So yeah, he has a very interesting blog. And with that, I'll get started. So I'm going to share my screen. And as usual, if you want to join these sessions, feel free to email me at mgreenb801@gmail.com. All right, so here is the first problem. Let me maximize. So we have a triangle ABC with in center I. Oh, Anmol, sorry, I didn't get that faster software yet for I guess recording, but I'll do it next time. So yeah, it's a short problem statement, although the later ones will get longer. So the in center is I and the circumcenter is O. So I'm going to draw the circumcenter. That's O. And I'll draw the in center. For that, I have to use the algebra tool. Or at least that's the fastest way that I know of. P is the reflection of A over OI. All right, we have Ruben Carpenter joining us. Just a second. Thanks for joining us, Ruben. And so A prime or P should lie on the circle. This problem actually looks pretty familiar for some reason. Maybe I did this before. Q is the second intersection of OI with the circumcircle of BIC. So we know by the in-center X-center lemma that that's centered at the middle of this arc. So I'll draw that in. So we want to show that AI, BC, and PQ concur. So let me make the diagram a little nicer. Just a second, so that we can see point Q. I don't want to make O and I too close together though. So I think that looks good. So this will be point Q. AI, if we draw that, it meets at the midpoint of arc BC. So I can call that M, I guess. So M is the circumcenter of the circle, or the center of the circle. We want to show AI, BC. So we want to show that PQ passes through this intersection point. Let me try to make the diagram a little better. Maybe, yeah, I think a figure like, so yeah, I want to make it, what's a good diagram? There we go. I guess that's okay. All right, let me hide a few things. So Sardar told me that he has seen this before. So if we get stuck, he can give us hints. Okay, so P is the reflection of A over OI. So AIP is isosceles, but and QAP, so these three all lie on the perpendicular bisector of AP. Maybe it's worth drawing, I'll just draw the midpoint of AP just to make it clearer. So yeah, this is the perpendicular bisector of AP. Does AI also bisect angle PAO? That is a good question. Let's see. No. So yeah, maybe I could just label this point right here. That's the point where they're supposed to concur. So yeah, it looks like there's some kind of symmetry in the figure. It almost feels like Poncelet's porism a little. I wonder if PQ is tangent to the circle. No. Yeah, it looks like there's some kind of reflection symmetry here. So AIP is isosceles, QAP is isosceles. So I guess we could let QP intersect BC at a point E prime. And then we could try to show that that AE prime is an angle bisector. That's another way to do it. Or maybe this is some kind of radical axis theorem. So BC is a radical axis. Can we make PQ a radical axis? So what if I drew these 2 points? I'm trying to make PQ a radical axis. I don't know if that will work. But I'm going to try it. Oh, it looks like AFMQ is cyclic. And then it would follow from the radical axis theorem. If so that's one way to do it. So we want to show AFMQ is cyclic. Let's see. We can ignore E from here on. Yeah. Assuming I try to solve it that way. Yeah, so I could still draw that segment, but yeah, just leave out point E. So yeah, let me hide the circle. Just, we want to show AQMF is cyclic. We could try to show angle IQF. We could try to show that that's half of angle IMF. Guess there's a couple different ways. So yeah, we know IMF is isosceles. Let's see. An angle IQF, it's the same as angle IQP, which is the same as angle AQ. So IQP is half of AQP, which is, and that's 180 minus. I think we might be close here.
Michael, it's kind of obvious because angle AMF is angle IMF. Is double of angle IQF because the arc the IMF see the arc of IF and M is the center.
Yeah. Okay. So AMF is twice IQF. Yeah. So IMQF is cyclic. Yeah.
So that's solve the problem. Oh, that's a nice problem, Michael.
So wait. AMF but we want to show, so AQF. So we want to show AQMF is cyclic, right?
Yeah, and but IMF is double is equal to AMF.
I see it now. Yeah. All right. I like it. So I will type that up.
It may be difficult if we can find the point F. It would be so much difficult.
Yeah. So yeah, the point F was pretty useful. I could delete point G. So I'll try to type it up quick because I know the later problems are going to be harder. So let AI meet the circle ABC at M. And then by the in-center X-center lemma, M is the circumcenter BIC. I've been using that a lot, in-center X-center lemma, lately. I'll just say M is the center of circle BIC. And then let the ray QP meet the circle BIC at F. And then we could do the angle chase. So we have angle AMF equals angle IMF is equal to twice angle IQF, which is equal to angle AQF. So that's I'll just say, since Q lies on IO, which is the perpendicular bisector of AF. or I don't think it's AF, I think it's AB or AP, whoops. All right. And then that means that AQMF is cyclic. And so then by the radical axis theorem, AM, BC, and QF concur. And so that means that AM, BC, and PQ concur. All right. That was a fun problem. And I see some people in the chat. Serdar found another solution using projective geometry. So if AI meets BC at a point T, then AT, I, and X center are in harmonic conjugation. That's a well-known fact. And since angle I, IB, so since it's a right angle, so yeah, so you'd have to draw this point over here, or an ICI, so QI bisects angle TQA. What is, so TQA? Oh, but we know this is an angle bisector. So IQIA.
No, it's not. We are trying to prove that QI is angle bisector in TQA. It's different. It's not PQA, TQA.
Oh, TQA. I see. Hold on just a sec. So T.
Yeah, T is that.
And then once you know that, you know it's also the angle bisector PQA, so that would prove it. Interesting. I like it. All right. That is it's an interesting solution. So I'll move on to the next one. All right. So we have a triangle with circumcenter O, orthocenter H, altitude AD, and median AM. All right. So I just learned recently that you can just use this midpoint tool to take the center. But for the orthocenter, you have to use the algebra tool. So we want this to be O. And I'll just label this, sorry. My keyboard double clicks a lot. So this we'll call M. The altitude is AB. And actually, let me just draw the orthocenter first, because I could use that. So H is the orthocenter, so that's triangle center 4. And then I will draw the altitude AB. So we know AH is twice OM. The line through H perpendicular to AM, so that's the Humpty. That's kind of how you make the Humpty point, right? And it meets AM at so P is the Humpty point, and Q, I'll have to draw that. So this is very similar to my video 5 on my channel. So basically, in that video, I used the point Q actually. So I think there's like a lot of cyclic quads here. OA and OD. Okay, so we want to draw the circumcircle BOC. And that circle also has a lot of interesting properties. Circumcircle BOC. So draw OA and OD. And that meets that circle at 2 points. So I'm going to have to zoom out a little bit. T and R. So yeah, this problem looks a little bit harder, or at least more complicated. That looks better. So this is T. This point is R. And S is the foot of the perpendicular from A to TH. And we want to show that P, Q, R, and S are cyclic. This is a very weird configuration. Let me see. On that point, it's hard to get it. Try one more time, and then there we go. All right, let's hide a bunch of stuff. Two, three, 4, 5. I'm gonna hide a lot here. There we go. And that, this, that. Is that everything? I feel like I'm missing something. Oh, AO and T. I want to draw that segment. There we go. So APHS is cyclic. Might as well, I feel like there's a lot of cyclic quadrilaterals here. So we want to show PQRS is cyclic. Do these concur right here? Let me check that. It looks like they do. Interesting. Okay. So it might be worth labeling this point right here. I'm going to delete the circle because we don't know that they're actually cyclic yet. We have to prove it. But it looks like that's
HT and BC is on that circle too.
The intersection of HD or HT and BC. So this
Yeah,
point.
HT and BC. Yeah.
Interesting.
And I guess EF is parallel to AD.
It looks like it. Do you know are you able to prove it, or but it looks a lot like it?
I don't know the proof.
All right, interesting. Yeah, there are a lot of points on that circle. So yeah, I know the circumcircle BOC, it has like a lot of, like if you do a root BC inversion or something, I feel like it does a lot. I don't know. So P is the Humpty point. what is the Dumpty point? I know like H and O are isogonal conjugates. BOC, oh, that's right. Yeah, BOC and BHC get swapped under a root BC inversion and then a reflection. So yeah, maybe that makes it easier. If you guys can figure it out, yeah, let me know. And where does P go to? Like, yeah, I'll draw the circumcircle BHC. Do you know where P goes to under that transformation? Okay, so we just haven't drawn the Dumpty point yet. But yeah, okay, so we know BHPC is cyclic because P is the Humpty point. Oh, I think the Dumpty point is you have to draw the circle with diameter AO, right? And see where that meets. I think that's how you do it. Yeah, I think it's where the circle with diameter AO meets the circumcircle of BOC. I think that's the Dumpty point. So not 100% sure, but I think, okay. Yeah, it almost looks very close to point H here, but it's not actually, yeah, it's not point H. It's, yeah, there's no point in drawing it here. 1 second, guys, I'll be right back. All right, thanks for waiting. Let's see.
Well, we can prove that QRO is 90 degree.
Angle QRO.
Yeah.
All right.
From QDBC is harmonic, and RD is angle bisector in BRC.
Okay, so QDMC is harmonic and RD
QDBC.
QDBC, I'm sorry. So yeah. And
RD is angle bisector.
RD is the angle bisector of BRC. So okay, so yeah, so that proves angle QRO is 90. It's a good find.
We can prove that EF is parallel to AD, and we can prove that 5-point are concyclic.
Okay, so QREF is cyclic. And
now we know that QPER is cyclic.
And QPER is cyclic. So yes, okay, so those 5 points are cyclic. So how do you know EF is parallel to AB?
I couldn't prove it.
Okay, but yeah, if we can prove it, then that would work. And then once we know that, so QPEF and R would be cyclic. Is ASRT also cyclic? Let's see. Yes. Interesting. So angle ART is 90 degrees.
Can you delete the circle with diameter AH?
With diameter AH, yeah, I can delete that. And I'll delete G, we don't need that. So if I'm trying to make H as an orthocenter. I don't know if it's worth doing that though. So if we know that Q, R, F, E, and P are cyclic, how do we show that S lies on that? Is it just an angle chase? Because we know like angle QPS is the same as angle HPS. And angle QFS is BFS. I think it might be an angle chase just to like once we know that Q, R, F, E, and P is cyclic, I think it might not be that hard to show S lies on it. Yeah, that would be an easy angle chase because angle SPQ is angle SPH is angle SAH, which is the same as angle HFD. So yeah. So all we have left is to show that EF is parallel to AB. I would bet that's like projective geometry. So you just have to find the right things to project through. So yeah, we know OM is parallel to AB. Yeah, maybe we could just use similar triangles. Maybe we don't even need oh yeah, actually, yeah, since we know angle ASF is angle ADF is 90, that's an even faster way. So we know ASDF is cyclic, and then therefore, since we know that QRFES is cyclic, yeah, that would prove it. But we still have to show EF is parallel to AB. But wait, we know that angle, actually, never mind. DE over EO and DF over FM. Which the power ratio lemma? Normal ratio lemma. So DE over EO is the same as AD over OM, and DF over FM. Yeah, how do we do DF over FM? I feel like there has to be some projection we can do. Can I let AO, yeah, I can let AO meet BC. How does that follow? We want to show DFMG are in harmonic conjugation. Oh, because you're projecting through O onto BC. So since FM over FD is GM over GD, this is OM over AD. Okay. All right, that makes sense. So I feel like we're pretty close with that. Maybe we could project through H onto, maybe not. Seems like projecting through T is maybe the most natural. Then it's, yeah. What if I project through O onto the circumcircle of BOC? So it would get R, T, this point. Yeah, but where would F go to? QDBC. So we can start with that and project through O onto the circle. So let's see where Q goes to. Q would go to this point right here, right? And yeah, I'm not sure what to do with that point. Maybe angle OID is 90. Looks like
It
it.
must be true from power of point.
That angle OID is 90.
Yeah, because we can prove from power of point that IDMO is cyclic.
Okay. So then we would have, so ID and OM concur on the circle. Okay, so we would have IR. Yeah, okay, that helps a lot. So they would concur at a point. And so if we knew that I forgot what we're trying to do, start with QDBC, and then we would get IRBC, and then we could try projecting through D. And then we get like, so I remember we discussed this before. So actually we just went in a circle, because if you take IRBC and you project through D, then you get BCOJ, and we know that's harmonic.
Other way is to prove that EG bisects AD.
EG bisects AD.
Yeah.
Are you sure about that? It looks like it is true. Interesting. Do you think I should keep point I, or try to prove it by Menelaus? Possibly. So I think anything that you can prove with Menelaus, you can usually prove with projective geometry. EG bisects AD is true because OM is parallel to AD.
Yeah.
That proves it. Oh, because OM is half of AH, right? That's what we're using, right?
No, it's from Cheva.
From Cheva. Because OM is parallel. So yeah, so GE by Cheva, GE bisects D. And then what were you thinking from there?
Well, I assumed that EF is parallel. I forgot that. We are trying to prove that EF is parallel to AD.
Interesting. So if GE bisected AD, Then if we let GE intersect AD at some point K, and we project AKD infinity onto BC, we'd get GMD, and then, yeah, so it goes back to trying to show that DFMG is harmonic. Yeah. We could also prove OF and AD concur on the circle. Oh, really? That would solve it? Yeah, I think I see why that would solve it.
But how to prove it?
Yeah. Because, yeah, we haven't really used point T. I feel like we want to project through point T or something. I don't think we've ever used point T. So maybe we could use that angle BTO as angle CTO. And we could do something similar. I don't know. I want to project through point A because DFM, yeah, the question would be where F goes. But D, M, and G, we kind of know more about where they go.
I think projecting from H is easier. A lot easier.
H would be easier, right?
Yeah, because HM and AO intersect on circle.
All right, so yeah, let me draw that. But H doesn't lie on the circle itself, but
Well, we project from H onto AT.
Onto AT, okay. So DMFG, so F, M, and G go to TI and G. Oh, so it'd be AGIT. Oh yeah, that's pretty nice. And then once we have that, we just need to show AGIT is harmonic. And maybe we could just use angle bisectors because angle ACI is 90 degrees. Can we show that CI bisects angle TCG?
Yeah, from angle chasing we can.
Okay.
Because IT is angle bisector in BTC. And we know that BIC equals to 90 plus half of BTC.
All right, so we'll start writing it up. Okay, so what points did we introduce? F, let TH intersect, oh, yeah, let TH intersect BC at F.
Well, we didn't finish the problem actually, but we are close.
But we showed AGIT are in harmonic conjugation,
Yeah.
and so then that proves DFMG are in harmonic conjugation.
Yeah, the remaining one is S, point S.
Oh, point S, that is the perpendicular from A to TH, but it's not hard to see. So we showed that Q, R, F, E, and P is cyclic because they're all right angles. And then it's just an angle chase to show that S lies on that. Yeah, so the angle chase I did, so angle S SPQ is the same as SPH, which is the same as SAH. And SAH is the same as HFD, because SAH is 90 minus SHA, and that's HFD. So we have SPQ is SFQ basically.
Yeah, nice.
All right, so I will type that up. Let T BC, and then I is AO intersect ABC. And G is AO intersect BC. So just defining our points here. Those are not mentioned in the problem. And then, so first, we are going to show that AIGT is cyclic. And so we know angle ACI is 90 degrees. And then BCI, we want to show it's the same as angle ICT. I just forgot how to do this. But wait, you just mentioned, so you know IC is the angle bisector of GCT. You mentioned that was an angle chase, right?
Yeah. It comes from that TI, the angle bisector of CTI, and angle BIC equals to 90 plus half of angle CTB.
CTB. Oh, because this is an angle bisector. So
Yeah.
basically I is the incenter. It's basically, yeah, incenter X center lemma. So, okay, yeah. So, okay. So by the incenter X center, I'm just going to copy what Hakan just wrote. And then, so CI bisects angle BCT. And then also since, since angle ACI is 90, that means that AIGT is in a harmonic conjugation. AIGT are in harmonic conjugation. And then we projecting through H onto BC. Then we have D M. Just want to make sure I get the order of this right. So AI, G, and T are in harmonic conjugation, and if we project through H, that would mean D M DMGF are in harmonic conjugation. I don't know if I'm writing these in the right order. So yeah, correct me if the order is wrong. And then if that's true, I know there were like a couple ways. So Hakan wrote like one way using ratios. I think then we can project through E. So, and then since GE bisects AD, that solves it. So that's one way to do it. Let's see. So I'll just write out, I think what Hakan said might be the best way to show the parallelism. So FM over FD. Yeah. So we have that. So first I'll just say OM is parallel to AD. And so that means that we have the below, which means that EF is parallel to AD, which means that EF is perpendicular to BC. And once we know that, so now it's just an angle chase. So angle EFQ is angle ERQ. But we also had to show, yeah. So BCDQ is harmonic. So that's well known. Let me see if there's like a quick way to explain why. Is that like Ricard's theorem or something? Let's see. Well, I guess if you project through H, then you would get yeah, why are they in harmonic conjugation? It's probably not very hard, but trying to think of the easiest way to show that. So I know one way to show it. You could let BH, you could draw the BH and CH, and then it meets it at 2 points, and you could show that I'll just say see video on IM lemma. I'm sorry, on the HM theorem. But it shouldn't, if you watch that video, I think it shouldn't be hard to prove it. I don't know if there's a more obvious way. So if you guys think of it, let me know.
Well, we have QB multiplied by QC equals to QD multiplied by QM, and M is the midpoint of BC.
Ah, okay, that works. So QB times QC is QH times QF is QD times QM. So I'll just write that out. QH times QP And then projecting through, so we know RD bisects angle BRC. Since O is the midpoint of that arc, and so that means that angle QRD is 90. QRD, which is angle QRE, is 90. And then we also have angle QFE is angle QPE is 90. And so that means that QRFEP is cyclic. And then an angle chase shows that S lies on that. So I'll just finish with that angle chase. So we know that APHS is cyclic. So that means that angle SPQ is SPH. This angle SAH. Which is angle HFD, which is angle SFQ. And that implies that QREFPS is cyclic. All right, that was a nice combination of ideas. A lot of stuff going on here. We use the fact that RD is an angle bisector to show that these are harmonic. Prove that RT, BC, and the tangent at A to ABC are concurrent. Interesting. We'll have to check that out sometime. All right, so I will move on to the next one. So we have a triangle ABC within circle omega. Whoops. I is the end center and D is the tangency point with BC. Might as well draw E and F too, right? So B, E, and F. So S is the Sharkey double point. So we see where does the circumcircle of AFIE. So inversion is often very useful in these problems. So, whoops, sorry. So I want to close this. So this is point S. And often it helps to invert about the end circle in these kind of problems. So H is the orthocenter of triangle BIC. I feel like there's something special about the I feel like I've seen the orthocenter BIC before. Anyways, so I'm going to use GeoGebra to draw it. So H is the orthocenter. Oh, it's all the way up there. Wow. Q is on HS. So that AQI is 90 degrees. Whoops. So another way to say that is I is the orthocenter of HBC. So AQI, so it's where it meets this circle, right? So this would be point Q. This drives me crazy. It keeps double clicking. So this is point Q. And let me see who else is still on. So and then X, so let X be the reflection of I over the midpoint of BQ. So basically IQXD is a parallelogram. Hold on just 1 second. Or I'll reflect about the point. And I will call it X. So it looks like that lies on the circle, on the end circle. I don't know if that's obvious. Oh, that's the problem. To prove it lies on the end circle. Okay. So interesting. Let me hide some stuff. So I is the orthocenter of HBC. So HI and D should be collinear. Oh, is this problem trivial after inversion? Or AD is HD is perpendicular to BC.
They are talking about
The other problem. Oh, they're talking about what Hakan proposed. The one Hakan just said. Okay. Interesting. So yeah, I'll delete point X for now just because we don't know. But yeah, it basically says, so G is the midpoint of QD. So yeah, it says if you find the point X, which makes this a parallelogram, then it says X lies on the end circle. So I mean, what we could do is we could draw the parallel through Q to HD.
And make the angle BAC less, because when H is inside, it looks better.
It looks better when H is inside the circle. So kind of like this. All right.
Well, you should draw it again. That's it.
Let's see. Yeah, because it disappeared. So let's see. Yeah, I'm gonna have to draw some stuff again because of how I did it. Whoops. So This would be point Q. And so we want to show that there's a point on this circle so that IDQS is a parallelogram. That's kind of interesting. So I wonder, does it have to be like, it feels like what if I draw the perpendicular to ID? So like this point right here, are we saying that IDJQ is a parallelogram? Oh, not necessarily. I don't think it's necessarily point J, right? But it makes me wonder. Or is it? No, because now it starts to get slanted. Yeah. So if Q is here, for example, but then we're saying then it would be like this point down here. Okay. So yeah, what does that mean? Is there anything we can say about that point that makes a parallelogram?
Will it intersect if and BC? If and BC.
Let's see. Sorry. Let me make it so that it doesn't look like it's tangent to that circle. Maybe that's better. So J, we're saying
The other one.
okay, so QKID is a parallelogram basically. Did you also want me to let it intersect EF?
EF and BC.
EF and BC. So here's the intersection point with BC, right? Oh, you're saying just draw those two. Okay. Whoops. So BDC and M are harmonic. It is the intersection of the end circle. Yeah, and the perpendicular from Q to BC. So we want to show QKDI as a parallelogram. It's a very weird configuration, but I wonder if QS passes through. No, I don't think QS passes through that point. Let me shorten some of the lines. I don't think this is true, but I wonder if BD is equal to LC. No. So SD and AI meet on the circle. That's part of the Sharkey double configuration. It almost looks like it passes through F in this figure, but yeah, I don't want to make it look like it passes through F. Then that looks okay. So yeah. Is BIKC cyclic? No. So yeah, this was problem 3 on the first day. So I don't know if that means it's harder than the rest. It's hard to tell.
And delete other points except K on the QL.
Delete. Oh, so delete point J and L.
Hide or hide, delete or hide.
Okay.
Just K is the point.
Yeah. Do you want me to keep point L? I'll keep
No
that.
need, actually, we can hide the line also.
So just draw QK, I guess, right?
Yeah.
Okay. Yeah, what's special about point K? We want to show QK as the radius of the circle. I don't know if it's worth drawing a circumcircle BHC. This KQ, I wonder if, okay, I'm gonna erase it right now. This KQ tangent to that circle. No, I don't think so, because I think I saw it before, like sometimes it's like slanted. No, so yeah, it can intersect the circle. And also, yeah, we didn't draw the center of the big circle, but SI passes through the antipode of A. Does KQ equal KI? Yeah, that would have to be true if the problem were true, because we want to show ID KQ as a parallelogram. So that would mean KQ is equal to ID, which is equal to KI. So yeah, maybe that's the way to go. Yeah, we want to show KIQ as isosceles. I kind of like that. Yeah. Is IK perpendicular to AI? Looks like it. So yeah, maybe that's how we should define point K. Like, is that always true that it's perpendicular? No, because like, yeah, that's not perpendicular. Oh, if that were true, yeah, KQ would be tangent. Okay.
A is the Feuerbach point.
A is the what?
Feuerbach point.
Feuerbach point. Really? Of what?
the triangle ABC.
A is the Feuerbach point.
Okay.
Isn't that like where the 9-point circle is tangent to the end circle?
Yeah.
Oh, K is. I thought you said A is.
Yeah, I
Really?
said K.
K is the Feuerbach point. That's really interesting. So basically that means I'm going to draw the 9-point circle just for the heck of it. That's very surprising. Wow, that's so random. You just played around in GeoGebra and saw that?
No, actually, I saw it on the blog. I didn't read the solution, but I
Ah,
saw that he found so many properties about Feuerbach points,
interesting.
and this is one of them.
Let's see. So yeah, what do we know about the Feuerbach point? I forgot the proof of it. I
And
think
name the intersection of HP and EF.
HP
HB.
and HD and EF. So right here. I'm sorry, this point. HB and EF. Sorry. So yeah, I think Feuerbach's theorem, you can prove it using like inversion. You can draw that. Ah, it looks like it passed through K. Interesting. So we could let K be the intersection of the circumcircles of those two circles. We could define it that way. And then I wonder, are O and P the perpendiculars? So POD, how do we know that how do we know that BI and P are collinear? Is that obvious?
Iron lemma.
Iran lemma, okay. So I is the, okay. Okay, so we can define K to be the intersection of those two circles. Then we'd have to show that QKID is a parallelogram. So could we show angle KDI is angle QIH, or KDH is QIH maybe? And then maybe we could show angle BID equals angle, yeah, I'm just guessing here. Maybe we could show angle BID as angle IDK. The Feuerbach points of BHC. Wow, this is pretty crazy. This is some deep math. So yeah, we mentioned that K lies on the 9-point circle of both. So yeah, that kind of makes sense. Oh, but no, because K, I don't think so. Yeah, because K doesn't lie on the inner circle of BHC. Yeah. We want to show that AQ is parallel to the Euler line. Really? Okay. So let me draw the center of that 9-point circle of BHC. Or I could just use the midpoint tool, actually. So if I draw the center of this, so we want to show AQ is parallel to IR. It's interesting. We want to show that DK is perpendicular to AQ. So AQ is perpendicular to IQ. Is KP parallel to AQ? It looks like KPIR might be a parallelogram. No. But I'm confused. Why do we want to prove DK is perpendicular to AQ? Ah, that makes sense. IR is perpendicular to DK because they're both the centers. I don't know if it's worth drawing the circumcenter or the circumcenter of BHC. Oh, yeah, you just said to do it. Okay. All right. So, okay. So here is the T is the circumcenter, and U is the midpoint, which lies on the 9-point circle. Whoops. Looks like Serdar got cut out for a second. So T, yeah, I and T, there are on the Euler line. And we want to show AQ is parallel to that. Angle HSI. So angle HSI is QSI is QAI. Is HS tangent to that circle? Let's see. I think it might pass. I wonder if it passes through the, well, no, that would break the symmetry of the problem. No, it's not tangent. Yes. Let me move this out of the way. Oh, EF, sorry. So yeah, instead of V, I want this point. Whoops. There we go. We know that DK is perpendicular to IT. I think that would solve the problem if we knew that. Oh, actually, yeah, we do know that. But we still need to show. Yeah, it depends how we define things. So AQ is perpendicular to IQ, and we want to show DK is parallel. Yeah, it remains to show AQ is parallel to IT.
Can you intersect QK and AN?
Yes. So you want this point?
Actually, I cannot see this point. Okay, they don't intersect on circle. I just
right?
wanted to see that.
Can I draw IS and intersect it with EF? So that's the Sharky Devil point, right? So D, I guess S is the Sharky Devil point, but we have, oops, DW is perpendicular to EF, right? That's the Sharky Devil configuration.
Are VPT collinear?
Or what collinear?
VPT.
So VP and T.
Yeah, they are not okay.
But yeah, DW is perpendicular to EF. I don't know how much that helps. So DW is parallel to AI. Let's see, I keep forgetting what we want to prove. So we want to prove IT is parallel to AQ. Can we show angle QAI is angle TIN? I don't know. This probably makes my brain hurt. TIN is TN. TIN isn't, I don't think it's equal to TNI. Is oh, yeah, it's all right. But TNI, let's see what else we wrote, is QNI is DMI. So I could try. So is MI can't, so N is the circumcenter of BIC, right? And is MI the radical? Oh, is that right? But I'm just curious. No, MI is not like the radical axis. We'll spend like a couple more minutes on this, then maybe move on to the next one. I wonder if there's some homothency. So we want to show they're parallel. Yeah, it is a weird definition. I agree with you. Yeah, it's a short problem statement, but it's looks like a deep configuration. It's hard. All right, I think I'm gonna move on to the next problem. That's okay with you guys. We can come back to it in the end. All right. So here we have a triangle with in center I.